Hello everyone, my name is Neha Dikshit and today I'll be covering a subtopic convolutional neural network feature mapping. In today's discussion, we'll start with why do we care and what's the impact of computer vision or how can computers see. We will also look into understanding a convolutional neural networks and the feature maps. When we talk about computer vision, the first thing that comes to mind is how do machines get vision? Vision is a very important part of our lives. It helps us recognize objects, behaviors, etc. The AI vision has been bridging the gap between humans and machines. Today we see self-driving cars where the image is taken as input and the vehicles try to learn to drive based on the images or the pixels coming in as input. Computer vision algorithms recognize the patterns in fields and determine the presence of diseases. Weed identification systems have been developed that combine computer vision images, satellites, drone imagers. Computer vision enables the detection of early symptoms with high certainty and is able to recognize patterns, which is of great help in medical field. Now this brings us to the question, how do computers process pictures or pixels coming in form of images? To find the answer to this question, we need to understand how a computer views a picture. To a computer, an image is just pixels. For example, on the screen you currently see a picture of Abraham Lincoln. This is made of pixels. Since this is a grayscale image, each of this pixel is made up of number. Computer sees it as a matrix of two-dimensional numbers. Now, in order to identify this image and then label it as whether it's President Lincoln, Washington, or Obama, there are two ways to approach this problem. In machine learning, we call it classification, where the output is taken as labels, or a regression problem, where the output continues to take continuous value. So we want to predict a label of this image. In order to correctly classify, we need to know how do we uniquely identify this image of President Lincoln, Obama, Washington. So what are the unique features of the individual image that would make them, let's say, President Lincoln's image or Obama's image, Washington's image? So in other words, we are looking for key identifying features. And to better understand this, let's say if we are doing classification, we detect the key features like eyes, nose, mouth, and we use our knowledge about human faces and we build a detection pipeline to detect these features. The issue here is that how do we detect a nose, eye, mouth, considering there's so much variation that happens in an image? I mean, it could be as simple as the illumination variation. So feature detection is really difficult and we need to come up with something to do a better job at this. The better approach is learning visual features and then basically their hierarchies to see like what is that constitutes a final class. So in order to kind of do that correctly, we take a two-dimensional image and then we collapse it into a one-dimensional vector and then feed it through a very dense network. So let me explain this through an example. Now on the screen, you are looking at an image of X, alphabet X. So the problem statement here is how do we classify X as an X? Even though if you look at the image on the right side, it's kind of a little shifted, shrunk, and deformed. So if you look on the left side, uh, in this picture, we see the black boxes are represented by a -1 and the white boxes are represented as a +1. So if we were to compare the left side and the right side, we will not be able to say like left hand side is equal to right hand side. However, the right hand side is still an X. So for a computer to detect that it's an X, we have to come up with a better algorithm to handle the variation. So what we do here is we identify the important patches and map them as a feature. Each feature is a mini image. So as you can see on the screen, on the left hand side, we had broken down that X into each of these individual features. And as I said, like each feature is a mini image. So you can think of that as a two-dimensional array of numbers. And then we use these filters, these smaller matrices, to kind of uniquely identify and then further dense or collapse it and then feed it as an input to the next layer. So if you look at the picture on the screen right now, we will place the patch on top of an image and then we go ahead and multiply element wise. The final result is what we kind of sum it up, and that's the output that goes to the next layer. So if you can see in this picture, it's a 3 by 3 block that we have of ones and minus ones, and then we have an original image. This 3 by 3 filter or patch gets moved over the entire image. So let's say it's when it's put on this green highlighted box, each element is multiplied with its overlapping element. So in this case, if we multiply this 3 by 3 patch with uh, the green highlighted 3 by 3 patch in this picture, the end result is all ones. So it's a 3 by 3 matrix of all the ones. And that result is then consolidated, it's all summed up, and the output is going to be 9. So likewise, this 3 by 3 patch is moved over this entire picture, and then the output of each of these are consolidated and summed up and is fed as the input to the next layer. So as you can see that feature map reflects where in this image we actually need the activation. So changing the weights on the filter, we can change what the filter is going to be activating. And this is a core of computer vision network. To summarize, convolution is a key element of many computer vision algorithms. It is a process where we take a small matrix of numbers, we pass it over our image and transform it based on the values from filter. Subsequent feature map values are calculated according to the following formula, where the input image is denoted by F and the filter by H. The index of rows and columns of the result matrix are marked with M and N. We perform multiple convolutions on an input, each using a different filter, resulting in distinct features. We then stack them all, and that maps back to the final output of convolution layer. Are the references that have been uh, referred to while putting together this presentation. Thank you so much.